the C++ is such a tight-knit community, and it's awesome to have events like this where everybody can kind of immerse themselves in, mingle, and then get to know each other on a social basis and on a professional basis, while having some really good content that you can learn from as well.
Thank you for coming. I'm Kris, and I believe that metaprogramming is a superpower. And today, I will try to share a bit of that with you. Notice I didn't say template metaprogramming, but we'll get to that. But before we'll start, let's just make it clear what we'll be talking about. So template metaprogramming is the ability to generate code at compile time. There are many, many different ways to do it. One of them has been chosen by Cplusplus. That's why we had templates from the very beginning, and that's the first TSS here on this slide. But that's not what is actually difficult or wrong with C++. STD vector of T, specialization, templates, that's totally fine. Nothing wrong with that. That's the design which we have. However, what we'll be talking about today, and this talk is about these TSS ellipses, and these meta functions, this ability to manipulate things, ability to change these types, get something out of them. And there's a lot of power in that, which I'll try to show and then improve upon. So hopefully that sounds exciting. But before we'll dig in, raise your hand if you think that template metaprogramming in C++ is either too hard or could be easier. Okay, well, notice that these slides were pre-compiled with compile time as well, so I have the answer. So I totally agree. It's hard. But on the other hand, while we're dealing with all of that, while we do all of these hacks, therefore, who is thinking that template metaprogramming is actually powerful? Thank you. We're on the same camp. Therefore, I believe that template metaprogramming could be easier, powerful, still get nice error messages, compile fast. Who would like that? Everyone. Sorry, out of luck, it's C++. But we'll see how far we can get with that. So before we'll show examples, I just wanted to point out Sean Baxter gave a keynote at Cplusplus Now 2022 about metaprogramming in Circle. He's the author of this compiler, saying better metaprogramming features make better libraries. And I think that's the very, very important point about metaprogramming. It's not about your production code and stuff like that. It's about making the libraries better. C++ is great if it comes to making libraries, but making actually the subtle things and better interfaces, more performant things requires metaprogramming, because we have templates. And without great facilities to do it, that's kind of difficult. So without further, let's dig in. So I'll show a few examples of where the template metaprogramming is being used and how it's being used. So we don't have to dig far. Let's look in the STL. So that's libc++. I just taken it from the it. It's a variant implementation. It has this find index, where we have the T, and we have this TSS ellipses. And we want to get the index of the TSS which match the T. Very simple in principle, kind of difficult in metaprogramming world. There's a lot of solutions to that, which I'm not going to show. But you have to be kind of clever to make it happen. So that's one of the examples. And standard template library is full of that. Another thing, who likes tuples, using tuples? I believe your compilation times are exploding. So std tuple is an example of that. So before Cplusplus 26, when we get pug indexing, that's usually implemented with template recursive instantiation, which is the worst kind of way of doing template metaprogramming. That's example of lib standard C++. Whoa. Sorry about that. Another example from Microsoft STL, array. Even array has template metaprogramming in it. You have to enforce the types to be the same. And there's tons of other examples, which I'm not going to dig into that, but you get the gist that STL is full of template metaprogramming. It's full of that. And why? Because it's a library, and metaprogramming empowers libraries. But there's an observation. Standard template library doesn't have a standard template metaprogramming library. I don't know whether you have noticed that before, but that's true. All these, all implementers of standard STL are very powerful implementations, but very tricky to make it right. And they lose a lot of magic to do it. By the way, there has been a proposal to add that to the language. That's by Peter Dimov, the author of Boost MP11, great library, by the way. Didn't get through because of Cplusplus trying to get into different directions, which we'll actually discuss. But very interesting point, I think, an observation that STL on its own, although it has tons of template metaprogramming, doesn't have facilities to actually do it. Therefore, implementers have to deal with intrinsics and hacks to make it happen. Another thing, which is really close to my heart, is performance. And metaprogramming empowers performance. So in that case, let's just look at the simple example of unpacked struct. Shout what kind of size that will be. What will be the size of? 12. That's right. For those of you who don't get it, we can read it in the standard. But the point is that it's not optimal. And if you follow data-driven development or something like that, the data-oriented design, you may be surprised. Wouldn't it be nice if you have a meta function, for example, pack, which will pack it for us. Like it will do the unpacking of the struct and pack it back. That's powered by template metaprogramming. And if you have reflection, we can even get the same names out of it. Before the reflection, we could get the tuple out of it, which is packed. But with the reflection, we can get the names as well. So that's very powerful. That gives us better cache utilization and stuff like that. So performance is important. Therefore, I'll have one other slide about it because I care so much about it. So I claim that way more things than it's assumed by default and by most projects is not at compile time. And that hasn't been leveraged as much, I believe, because of the facilities which we have so far. So for example, let's look at these protocols. We would like to, at runtime, look up which string view is matching to the protocol and return an enum. Very simple thing. But if you get into the implementations and overhead, you'll see that it's a lot of code to make that happen. But what I'm trying to point it out here, that if you have policy design from Andrei Alexandrescu, design by introspection, you can make choices based on what you care about. You care about performance, you care about the size, you care about the memory. You can make that choice yourself. And just to scare you a bit, I will show a bit of assembly, because I think it's extremely powerful that this magic loot, which is the magic lookup table, if you're interested how that works, you can poke me afterwards, I will show you. But notice that the first implementation on the top doesn't have even the lookup. It doesn't have a table. All of that is in the register. So it's the smallest hash table you can get. There's no lookup, no comparisons, nothing like that. It's just a few instructions to get that mapping from these protocols to the enum. And the other one, it requires an additional lookup table. So you will have cache misses potentially and stuff like that. So I think that's powerful. And finally, as an example of metaprogramming to get you excited about, I just wanted to point out about state machines. I love state machines. I think they're very powerful. But it's kind of hard to implement them very efficiently. If you go to the switch case and other solutions variant, you will get this overhead. But let's imagine that we have these states here, which do not have actually values. I would like the size of this connection state machine to be 1. Ideally 0, but 0 is not possible in C++, but 1 is, and it is empowered by metaprogramming. So I think that's great. And if you are inspired, and I will warn you that that might be a journey which you will hate all of, you can dig into metaprogramming libraries in Boost. They are very powerful, and as I pointed out, it will be a love-hate relationship, but I encourage you to give it a go. Okay, so that's the motivation. That's why I'm talking about it. That's why I care. But let's just look briefly what we were talking about. So a bit of history. So metaprogramming started from the very beginning of C++ because we have templates and they were abused, as pointed out in the keynote on the first day. But the first kind of libraries were like Boost MPL, which has been adapted with MP11, which is a great library, as I pointed out before. Then we had this heterogeneous stuff with Fusion and HANA, kind of a std tuple approach. And that has been great. Louis Dion did a great job with Boost HANA. However, that doesn't scale. It doesn't compile fast enough. It's not scalable enough. That's why today we'll be talking about value-based template metaprogramming. We'll show the MP, which will be the implementation in C++17, just for everyone who is stuck with that. And I will also show C++20. Although slides will be C++20 because the slide where C++17 is just less expressive. We'll follow up by reflection, how that actually mapping to what we've been doing. And we'll also point out the circle line, because I believe that this meta model is also very powerful and have different trade-offs. We'll show the benchmarks where the trade-offs are. And for everyone who is interested in metaprogramming, I really encourage to take a look into Ziglang and CompTime. That's a bit different approach than C++ is taking, but it's very extremely powerful and it's worth knowing if you care about those things. So hopefully that sounds exciting. Let's try it. So I'll build with the examples. I think I learn by examples. So I'll try to show more and more complex examples. I believe the first few examples, everyone can do it with a bit of help. But the further examples will be really hard to do in the current state-of-art template metaprogramming. So let's try it. Find index. As I pointed out, that's using the STL variant. So we have find index, we have T, and we have TSS, and we try to find an index of it. As simple as that. Like, I don't think you can get much simpler than that. But implementing that in template metaprogramming world is not that trivial. And making it fast to compile is even harder. I don't know, raise your hand if you can't do it and make it fast to compile. Okay, for the record, not that many people. So yeah, that's a great audience, thank you. You're in the right room. So how I would go about it? So I don't know much about template metaprogramming, let's assume that. I do find index, keep it simple, stupid. And notice here I introduced this magic. It's not a new keyword, although it could be possible with the UTF. I'm not going to do it, sorry. If you like it, maybe, but we already have carrots and other magic like that, so let's stick with something usually replace. I just put it as a placeholder. So what do we want to do? We do an array of this TSS dot dot dot, or ellipses. Nothing really scary here. And then we want to do a for loop. For loop, no template for, not if cons expert. If it equals, and then return the index, otherwise return the size. Simple? I believe that's simple. I believe you cannot get much simpler with C++. It's just C++. But there's a bit of magic here, right? What is this magic? So let's introduce a bit of magic to make that happen. So in order to do so, let's do, I like meta keyword, a meta name for it, because it's meta programming. So in my opinion, it makes sense. People from reflection have other names for that. Not important. So how we do that? We have the type, and we want the type ID. And the property of this type ID is that for the same type given, it will return the same value, and for different types, it returns different value. But it will be the same common type under the hood, which is the important part. So we care about this common type because we want to have it in the array, right? So we don't want to use the tuple. That's the base premise about value-based metaprogramming. Not tuple, not heterogeneous, but vector arrays, homogeneous stuff. So you could do that with C++11. I actually check it. Clang 3.1 compiled code to the level that you have to do a bit of magic, but the idea is simple. We have the address of the function, and that will be different per different translation units and compilation, but that doesn't matter because it's unique for the case which we need. So that's the first thing which will allow us to do that. Is that enough to do our find index? Well, actually, if you take a look into that, let's go back, find index, array, meta of TSS ellipsis, for, okay, I don't have to show or explain that. Static assert, we're good to go. It just works, right? So that's the first use case when we have the templates and we want to get to the values. But you can say, Kris, that's like for loops, ifs, that's not modern C++. And we have these types as well. So let's refactor it a bit. So notice here that instead of templates, I just use auto and range. Just move it to the value space instead of types, because why not? We want to have it as a cons expert, which is important. We'll talk about it. Function. And the implementation is the same. But because of this small change, we have this capability to use it with numbers or any other types, right? That's a simple function. We can notice that it's cons expert. We can run it in the debugger at runtime. We can test it. There is nothing really difficult about it, nothing which we don't know so far. We can get the code coverage. And we can fake it. So that's exciting, in my opinion. But let's go further. We have STL, we have ranges. Let's just do one more refactor. Can we use STL with that? Well, yes, we can, as long as it's marked cons expert. Any STL or any other libraries are available for us. Would that work? Yeah. There's nothing special about this code as well. But what is special is the question. So let's think about it for a second to maybe give you a hint, and I want an answer, and that will be immutable until we'll see the results. So knowing that STL is very well optimized for different use cases, right? It's really performant, relatively speaking. But also that cons expert is actually an interpreter for the abstract C++ machine. Therefore, it has some trade-offs because of that. Who thinks the raw loop refactor will compile faster than the raw, whether the STL will compile faster than the raw loops? Not a lot of people. Who thinks otherwise? Way more, okay. Well, I don't know. We'll see. Okay. So that was first example, quite simple. We have a types and we wanted an index, a value. Let's do something more complex because we're in the type space. We have the types and we want the type back. That's a bit more tricky, right? Because returning a value is easy because it's just single type. Returning a type is different because it's a different type. We can't return a variant because we still have to know which one is it. We want to return this direct type. So that's the tuple element. I believe everyone, or at least some of you, have seen how that's been implemented in STL. That's usually a recursive template instantiation until C++26. That's very slow to compile, and not much to say about it. But the way we can do it, since we have an array, we have a common type, let's do the meta, which is the new function, ellipsis, and we'll just get the index of the element which we want. So that will give us the common type of that index, right? But that's great, we did that already, right? But how we get back to types? That's the tricky. Like, we're in the value space, we want to get to the types. So in order to do so, we have to introduce a bit of magic. That's a bit of magic. So let's go for that. We have to extend our type with, unfortunately, a global register in the compiler. We don't have other abilities to do that easily. We can use kind of hacks for the indexes of the TSS ellipses, but that's just local scope. We want that to have ability to do that in the global scope so that we can pass vector of these meta objects anywhere and just play with them. So that works in any compiler, and you'll see that. There's no that magic about it, besides it's called friend injection. It's allowed in P2996 as well for good or bad reasons. But the main idea is that we return ID, which is the value, and we also, while it's doing that, register the ID to type in our global compiler state. And then when we want the type, we get this ID, which is the value kind of at runtime, but in context per context, and just get back the type, which we registered where we put it through. And that's unique IDs, because we have this address to the function. And that just works. So we can write meta of int and just get the type of it, and that will be just int. And that just works. So in that case, we have the type of std array of nth element out of that array, and that's it. So the usage is quite simple. So on the top, you can see here, we have this type of, nothing really special, just works out of the box. If you are happy to be in the Clang 19 world, so far you would be able to use pike indexing, which is a very powerful feature. Unfortunately, we don't have slicing, we just have indexing in Cplusplus 26, but then you can do ts ellipsis index. It's the same as the other approach in that case. Obviously, that doesn't give us the whole metaprogramming facilities, but in that case, it's very powerful. And that's based on typepag element, which has been added to Clang exactly 10 years ago by Louis Dion. So shout out to you, Louis. And that's, by the way, because GCC didn't have it, GCC 14, up from like a month ago, actually implement that typepag element as well. It doesn't have this indexing, but if you care about compilation and performance and you need to be in the type space, your Boost MP11 will automatically speed it up in GCC 14 because it will figure out that typepag element is available. So thank you. Okay, so I believe that with maybe a bit of help sometimes, maybe with a bit of effort, most of you would be able to get to those two examples at some point. Maybe it would be painful with the tons of compilation error and frustrating, but I think it's possible to get there overall. I've been through that process many times, and it's not pleasant, but it's doable. But I believe that this example is actually a showcase where if you can do that in the template metaprogramming world, you can't be named someone in that world. Because we have to do a sort, unique, and other things in order to get this example which I'm trying to show. So the idea is that we have a variant for t. And this meta function supposed to return the unique list of TSS and without qualifiers for which T is constructible with TS. That's kind of a common use case in some limited space, but just to go through that with you, we have a foo, and foo is constructible with int and bar, and when we call variant for T with const int ref, R value and string view void, which is also important because that's always special. And we would like to get the end bar because foo is constructible with end bar. So that's the kind of simple, in principle, meta functions to write. Anyone can write it out of, just right now in gold bold in C++ using template metaprogramming. Ben? Okay, Ben says that he has the implementation already at compile time. So, okay, we'll verify that. Okay, but yeah, you can imagine that's difficult, although it's very powerful, right? Because we sometimes want to do manipulations, especially for the on the library side, to do things like that so that we can have better interface, performance, and stuff like that. So how we go about it? Let's do it in our const expert world. We have our variant 4 meta function, which takes the range and returns the range. And that's, if you're not familiar with that syntax, which is kind of awkward, that we have a concept and auto at the end, that just constrained result. So what do you want? Well, what I want, to make it simple, I want a vector of this magic to start with. Then I want to iterate. I want to check whether the T is constructible with these TSs, which I'm iterating through. And then I just want to push back the remove CBRef. And why I want to use the type traits? Just because they're available, so I don't want to invent the wheel with that. Although we could make it easier and write nicer functions. And then what I want to do, I want to sort it to be able to make it unique. And I just want to return that. And that's a meta function in C++20, but you can do that in C++17 these days, which I think it's way more powerful and easier to express than template metaprogramming. And if you get an error in that, you will see this code, actually this code, not template instantiation of 100 pages of code, whatever. So I believe that's very powerful from at least that perspective. So how we can do that? That was fast. So we have this vector of this magic. And this magic is nothing new so far because this meta thing which we implemented so far, which was this pointer to the function, whatever, doesn't matter, is implementation detail, might be anything, is a common type. So if you get it from void, so that we have whatever name, void is a good start because it's void. So that's simple, right? We have the property of that is it's the same common type under the hood. The type ID equals, which is the way you can do std is same since C++20 because that's const expert, will be the same. And that's important. That will be an info, and that's what we discovered previously. But more importantly, and that's the most magic I will have to show about the implementation details. So if you were scared so far, that will be a bit scary, but the usage will be fine. So we want to implement these meta functions to call the type traits. How we do it? So let's introduce invoke. I like invoke. Might be any other name. And doesn't really matter. What is important here that we have this T, which is a unique identifier. So this decal type of empty lambda. Not that important if you're not familiar with template metaprogramming. But that's the whole implementation. And the main basic idea behind this is that we have the void, which is the info already established, right? And then we know a value, which is the new value which we try to compute at runtime in the const expert context, right? And we just get the diff distance, so that will be nth elements, and we just do the dispatch table to the right one. So that will instantiate for all the templates so far being instantiated, and we just find the one which matches the info object which we are passing through. So that requires a bit of magic behind, and that's not the full implementation to be optimized for compilation times, because that will instantiate it for the whole templates up to that point. You can do it that it will only do it for the template which you added. But overall, and I will show the compilation times, you can make it really fast. And the usability of it, it's very good. If that's not understood, don't worry. This talk is not about the details as much as about the usage. But if you're interested, I will happily explore with you how does work. So going back to our example, we have the variant 4. We create this vector, std vector, which is in consexpert in C++20, but if you don't have it, you can write your simple static vector on in-place vector in C++17, which I will point into a direction. And what do we do? We have a for loop. Like you notice that's a common thing with the simple things. We have a for loop. We do invoke if constructible of t, and we push back the remove cbref. You can imagine that you can write additional functions to make it nicer. So you would have if is constructible, then you push back remove cbref. But the main idea is that it's just normal C++. There's no templates, nothing. There's no if consexpert. You don't have to know anything besides the normal C++ to make that happen. And when we do sort, if you have C++20 ranges, you can do that this way. And that's all. That's all what we have to do in order to do so. And you can test it. You can debug it. If you get an error message, it will be better than the template instantiations because you will get the error from that code. You can link to that code and figure out that the pushback didn't work. So as simple as that. I promise it will be kind of template-less. OK, but you know, let's say you are on the C++20 compiler and you would like to do the ranges because you like the new cool things. I'll warn you about that, but assuming that you like it, let's do it. Let's put nice functions, meta functions, as you call it, to do this invoke under the hood. And that's the implementation you will get. We get the range. We do the filter or is constructible. Then we transfer with the remove cbref. And we get the vector. You have to do that with the ranges because that's the lazy write thing. And you just return it. I know, it's like you can't get simpler than that if it comes to modern techniques towards value-based anything. So it's the same here. But I lied a bit because, let's go back to that because that's actually an important question. I already recorded all your answers, so I know everyone who said before, and I will count for that. But let's say right now we have ranges. We'll use STL before. But ranges, is that going to be compiling faster or slower? I bet you have your ideas if anyone actually used it. But raise your hand if it will compile faster. Brave souls here as well. So I encourage that. I assume everyone else is either sleeping or doesn't care or thinks it will compile slower. Anyone slower? I see. OK, I will spoil it. I won't disappoint you. It won't disappoint your assumption here. OK. So far we wrote this meta function, right? But I kind of lied. Because we got a vector back. I don't want a vector back. Vector back is not useful for me. I need types. I need a variant of TSS ellipses. And that's where the last thing which we have to have for our library for completeness. So we need something which will get our vector and will apply it to a templated thing. In that case, variant. So how we can do that? That's the goal. We have the magic of the variant and our function which returns a vector or whatever. All right. So in that case, we'll implement apply t, which takes the template class. Not that important from the implementation perspective. It takes the range as well. Notice that you can actually put concepts on a NTTP. I find that intriguing. Also, if you want to put const ref, that's a different semantics. It's kind of silly how does work, but despite that, let's take a look. How you do that? Well, we do the declaration, it's 20. So we do immediately invoke Lambda with index sequence. If you don't know index sequence, not that difficult. It just generates numbers for how many size you wanted it to do, so that you can actually expand and do the fold expression of that. And then we just do declval, because we're in the unevaluated context, to do the t, and t in that case will be the variant of range of NSs which we have generated. So what that will do, it will get our vector, our variant, and it will go variant, vector of 0, comma, variant, not the variant, vector of 1, vector of 2, and so on. So we will get from the value space to the type space again. Like we had a type of was for a single type. We have a value, get a type. Here we get a vector, and we want a type list, or a variant, or a tuple, or whatever. Okay, so when we apply it, just works. So we do apply t of a variant of this function, and that's it. No magic afterwards if you have a few facilities which you have to implement. But you may ask me, what about testing? I want debuggability. I want to test it. I want coverage. I want nice error messages. I didn't promise all of that, but I can say that we can get quite far. So let's have a test which runs at compile time at the runtime. Compile time gives us the ability that it will detect the leaks, no UB to a certain degree, right? That's great. So if we screwed up our function, we're already kind of in a better position than already at runtime. And then runtime will be used to get the debuggability, the coverage, and all the other things which we want as well of our meta functions. And then if we care about testing, which I believe everyone does, we can write a test like that, which you will have the vector, and notice that we can just push back to it. We can have a setup, we can do whatever we want. And then when it's just calling the function, and then we just, in that case, assert. You can do better than that, because assert is not the tooling for testing, but I just wanted to introduce anything new. But if you do spend a bit of effort, and the example I'll show later, you can actually get really nice error message with the value which you expected and was given across all the compilers besides MSVC, which crashed for me with that case. But you can still get it nice. And you always get the assert pointing to the code in this meta function, which is just a C++ code, not the template instantiation. So I think that's powerful. So far, just to sum up, I believe we make it easier. We make it somewhat testable. Const_expr, don't use const_deval, use const_expr so that you can do that in compile time at runtime. It's debuggable, const_expr at runtime, right? We can get the code coverage. We get nicer error messages. I don't claim it's awesome. You can use the asserts in your function as well. So if you have your meta function and you're trying to dig in, what is happening doesn't work, I didn't write the test, I don't do TDD, you can just do the assert and get it. Imagine doing that with template metaprogramming. That it's instantiated and you want to know what would happen at some point. I don't know, if you've done any TMP, I bet you've been there. It's kind of difficult. You can try to do the warnings, tricks, fun, but not very practical. So with that, I'll give you the code if you want to try it out. So this is implementation of what we said so far. It's 100 lines of code with testing and everything. That's C++17. So you can do it better with modern compilers, but it works on GCC, Clang, MSVC. And if anyone cares, it works on Circle. It has no dependencies. So it's zero includes, nothing. It's just pure C++ code from scratch. And that's still 100 lines of code. And if you like it, I can't say that you will, but if you like it and you like the usability of it, you can check out the MP itself. That's C++20, but it has way more powerful features on top of that if you want to explore and do more magic with TMP. And it compiles also very well because it has a lot of optimizations to make that happen, which I will show in a second. But OK, so far so good. I hope I kind of convinced you that we can do quite well. Since C++17, so it's like kind of back to the future. I know most TMP these days is template metaprogramming, but I encourage you to switch the narrative because the future is actually different. And C++26 will have a different future likely. You can never be sure with C++, but let's assume that. So it's also based on value-based metaprogramming, which is, you will see, very similar. And I made an effort to make it similar to a certain degree. But it also has these meta functions for introspection and generation for the reflection, which we won't talk about it. You can check Andrew's talk about it as well. Very powerful concept, especially the generation part. But how does it work? Well, so instead of this meta, which we introduced, we have this caret, whatever, reflection operator is called. You either like it or hate it. It was a single one, just not that long ago. Right now we have two. I don't like the two that much, but OK, that's what we have. So that gives us the value space. That's like the meta thing, which we discussed before. And then you have another operator, which is called a splicer, and that will get us back to types. So like we have this type of, that will be the type name of splicer. So there's no magic in it as well. I just made a comparison between what we discussed so far, so that if you grasp the concept so far, you grasp the reflection as well. So a reflection operator is just the meta which we discussed, nothing else. The info of this meta void is just decal type of the global namespace scope. It's the implementation detail, so it doesn't really matter. Type of is type name of the spliced thing. Apply is called substitute. I don't like substitute, so I called applied. Invoke has a lot of different ways to be done in reflection. It's kind of difficult with the current proposal to do mapping from runtime to compile time back. And that has been changing, but as it is right now, it's a bit more difficult. So let's go quickly through that. Find index. That was too quick. OK, if you visually remember, that's the same code. So if you have C++17 and use that, you can reuse that in 26 when you get it. The only difference will be that instead of meta, which you can implement using caret at some point, you'll get the same. So nothing hard here in the future. If you're ready so far, you'll be ready in the future. OK, type element. Kind of similar. Instead of type of, we have type name of the spliced thing array of the index, right? If you grasp the before concept, it's just different syntax. Nicer or less nicer, depending how you think about it. OK, the variant 4. So kind of reflection proposal suggests using ranges because that's C++20 and it's nice. So this code already doesn't compile because the test trait has been removed. But you can work around it. As I pointed out, the reflection is not really ready for those use cases that much yet. There are ways to do it, but it's not great, and it doesn't compile great as well. Also, for the sorting, you have to provide how you want to sort it, because the info itself here doesn't allow it, so you have to say how to do it. But otherwise, it's very similar. You have the same functions. You can make it the same code if you really like. So that's the future, whether you like it or not. OK. So how we do that for the, that's the meta function. And right now we're going back to type space because we need the variant. As I pointed out before, we like the templates, right? So templates stay in C++. The std vector of t stay in. Templates stay in. Metaprogramming is changing. So the metaprogramming here has been done with the meta function. And right now we're going back to types with this type name of a splice pin, of the substitute, of the caret, whatever. I love it or hate it, but that's what it is. So substitute is the apply, which we discovered before. It's kind of the same implementation, just in the compiler as opposed to in the library side. OK, so finally, I would like to introduce you, if you haven't seen it already, to the circle. Raise your hand if you used, know, or like circle lang. Not a lot of people. So I really like it. It's Sean Baxter who developed it. Extremely amazing guy. If you look and try to compare GCC Clang to this compiler, you'll be amazed what one person can do. So kudos to Sean. But it has a lot of things. It has member packs which haven't been accepted to C++. So you can do like language feature tuple. It has different metaprogramming model, which we will discuss. It has reflection. It has safety feature. It has borrow checker, which is actually going to be proposed for the safety. So a lot of goodies. A lot of things has been tried to be pushed towards C++ without success. So it's kind of a fork. It's not open source as well, which makes it less available, but it's powerful. So it will be a bit different syntax, but bear with me. So how you do find index. So Circle has this cons expr ternary operator, which is the conditional. So you can do t equals ts's, ellipsis, and double question mark is like ternary operator at cons expr time. And ellipsis is just the index sequence built in the compiler, and otherwise be written the size of. So I know it may be difficult to comprehend that immediately, but when you look into that a bit more after a while, it's kind of quite simple. Also, let's look at the tuple element. If you can. Tuple element. So as I pointed out, Circle has pike indexing. So that's by default. It has actually way more than that because it has slicing. It has all the Python things. It's like, anyone using NumPy? Yeah, so you can do like the same like in NumPy or Python. You can do all of that. Reverse, do a lot of things which you can do with the comprehension stuff. So that's extremely powerful, and indexing is just a small part of it. But here, I just wanted to show you the difference between metaprogramming models and the effort. Although with the different trade-offs, because it's a different language, right, and a different model. But notice how much space I have here to put it on the slide. The variant 4, which was the sorting, is constructible, all of that. So here you go. I will explain that because I can. So it's called imperative arguments in Circle. And the way it's done, we have if, which will be expanded at compile time. So notice that we start from the variant. We do then if is constructible t from TSS. If it is, we do TS remove CVRF because all the types has those meta functions. Then we expand it, and then we do unique and expand again. That's it. So quite simple, but different, right? As pointed out at someone at this conference, I think Andre said that C++ cannot handle, or shouldn't, a new language again. So that trades off here, that different metaprogramming model, which hasn't been accepted by C++. But I just wanted to open your horizons if you haven't seen that you can do it differently, and it's still very powerful. And why it's so powerful, We'll look into in a second. So, it's metaprogramming, it's template metaprogramming. It means nothing without benchmarks in that case, because if it's great, but it compiles forever, no one will use it, and it won't be adopted. So I've done a lot of benchmarks, tried to optimize those things, because I believe that's important. And I wanted to share that and share the thoughts where I think all of that is heading. So I hope you see that well. So I don't see it, but that's for the Clang P2996 compiler from actually this morning, because I had to run it through this night. It takes forever to do all these benchmarks. So Clang P2996 is a compiler implemented for reflection by Bloomberg. Daniel is doing a great job on that one. And we have here a few comparison between different options. So MP is what we discussed today. Type element is just a std tuple. P2996 is the proposal for the reflection. As I pointed out, it's still experimental. So okay, let me rephrase that. That has been improved a lot from a few months ago where I started checking it. So although it's not great yet, the trade, I don't show the trade line here, but the trade is going down. But you can see the P1858 is the pug indexing. So that's the way where you can do the max performance if you put it in the compiler. So if you put an intrinsic, you get that. If you go further with abstractions, you go slower and slower and slower. So usually, I pointed out that tempered recursive instantiation is the slowest, but somehow P2996 managed to beat it so far. But not great, but that will improve. Trust me on that one. And also MP is comparable with MP11 as well on that benchmarks and faster in the other one as well, which I'll show. So what we want to be on the lower part of this graph because I mentioned compilation times and number of elements. I just measured 100, but it showed 100, but I measured up to 1,000, and yeah, interesting results afterwards. But I assume most template metaprogramming use cases will have a lot of smaller number of elements metafunctions. So let's look at GCC. GCC is a perfect example why std tuple is slow, because its implementation doesn't use tuple pack element. Before that's GCC 14, but they didn't change it yet. So you can see that yeah, you don't want to have that. So if you switch to MP11 or MP, your compilation times will be much faster. Let's take a look at Circle. Circle is, by design, having everything in the language, so it's always faster, I can tell you that. I tried to beat it many, many times. I don't think it's not easy. Circle is written in the data-oriented design style. Therefore, it's very powerful and uses SIMD under the hood. So it's hard to beat because compile is hard to beat and cons experts interpret it, so not ideal. But you can see here that MP is faster than MP11 and the tuple is slow. Okay, but right now, hold on, because we will take a look into filter, which is just a simple filter over a range. We just grab every second element. And that will be P2996 with ranges, without ranges, and other things. So hold on. Okay, so that in seconds. You see the P2996 without ranges and ranges. So I kind of verified who said it will be slower and who said it will be faster. But yeah, if you thought that adding ranges with cons expert would be a good idea, you may be disappointed at this stage, as of today. So yeah, we want to be on the bottom. And you know what that shows? Like, I don't want to give you advices about metaprogramming, but if you use row loops, you will be much better off in this case. But you didn't hear that from me. Okay. So that will be improved, but it's not great at the moment. Hopefully it will be improved. Like, notice that you have to import the whole STL to do anything with ranges either way. Okay, that's GCC. Nothing really special here to see. It's kind of similar. I also compared the memory consumption, and you can see it on the benchmarks if you look at offline. But it's very similar. There's nothing really outstanding to see. Besides that, GCC takes more memory than Clang, and Circle takes a tenth of that. But also, if you notice, that's Circle. If you notice, like maybe after the talk, the numbers on the left represent, the actual values in seconds. So if you noticed that you can compare the compilers having the same code being compiled and how fast it is, and you will see that Circle is much faster than anything else out there. And I actually tested it against Zig, Rust, and other things, and it's just the faster thing out there. So kudos to Sean again. Okay, so a bit of observations out of those benchmarks, because, benchmarks, we have to analyze them. So at first, I would like to point out that Circle-Lang metaprogramming model is the fastest to compile all around. But it has different trade-offs. It's a different language. It is a language inside a language. It's Turing complete as well. It has all these other drawbacks. But if it comes to the compilation times and maybe the how many lines of code you have to write, it's the fastest. Type-based metaprogramming can be really fast. Boost MP11 is proving that, and other libraries as well. But it has to be done with aliases and built-ins. It cannot be done with template recursive instantiations like std tuple. And if you follow that, you will get pretty good compilation times. So don't use tuple, use MP11 for the template metaprogramming. Finally, value-based metaprogramming with STL, unfortunately, is significantly slower to compile than raw primitives. As I pointed out, any abstraction, because it's cons.expr is abstract machine interpreter, will cost compilation times. And it's not like anything from profile. You cannot profile those functions, by the way. If you have a cons.expr function and you want to figure out why it's compiling slow, you try to profile it, and like on x86 or whatever, and you won't get the same thing because you would have to profile it on the abstract machine of Cplusplus, which you can't really do. So be aware of that. That's kind of important to know that, I don't know. I think there's a, but I think there's a path forward with all of that. In my opinion, value-based metaprogramming has a lot of power. It's awesome if it comes to usability. It's normal C++, so it's great in that regard. But if you really want the performance, we would have to change the cons.expr evaluation from being interpreted to being JITed or being a plugin or whatever, so that we can leverage like SIMD or execution. Imagine that you have backend which can do compile time parallel computations, right? So we want that. And I think that will have to change in order to scale. Otherwise, we will get a language at some point which won't be able to compile much. But don't worry, everyone who should be aware of that is aware of that. And there has been work on that already. So just to sum up, since we have 1 minute, again, all of that, what I'm saying, is not for the production code, it's not for your daily usage. It's for writing better metaprogramming libraries. And that enhances all the features. The better metaprogramming features, the better libraries. So imagine that we have all these goodies and standard template library maintainers don't have to deal with hacking under the hood, how to do the find index, whatever. They can explore and explore more features. And also standard itself has been limiting complexity because of the metaprogramming under the hood, which has to happen because we have templates. And that ain't gonna change. So with that, I would like to thank you for listening. And if you're interested to explore further the topic, I encourage you to check off the libraries as well. And especially if you're interested, I did kind of, just for fun, implementing P2996 metaprogramming model with P2996. So if you just want to, be curious how to approach it, might be an interesting read. And that's the keynote from Sean from CVP, now 2022. And if you're really kind of nerdy about metaprogramming, you can take a look into the Ziglang comp time, which has a different approach. It has constructor parameters, and you can do a lot of magic with it as well. And with that, thank you. If you have questions, I think we can do it, but I don't know whether we can. Tell me.
Have you implemented std sort with raw loops?
Have I implemented?
So replacing raw loops with algorithms sometimes might require, a lot of code for the raw loop.
Right. I implemented std sort with raw loops as well. Yeah.
Cool.
Have you?
No.
Hi. Yeah, so in the earlier slide, you had this like meta and info object. And then I see you have like a function called ID, which returns void. And they have like an alias. So can you tell us like how does that actually work and how can you actually sort it with std sort?
Right, because it's just a value, so it's a pointer. So you'll have a unique pointer, so you can just sort them out of the box.
I see. So and how is the value like unique?
Because it's a pointer to a different function of the template. So you have different templates. So this ID is templated on the type.
Oh, okay, I see. All right, thank you.
I'm wondering, you said that some of the compilers are already working on changing the interpreter to a jitter. Can you elaborate more about it, or can we expect anything anytime soon?
I didn't really say that they are working. I said that they are aware of the issue, but I think the closer we'll get to C++26, the more aware and more work will happen because of that. But nothing, I'm not aware of any actual work happening at the moment, unfortunately.
Yeah, thanks for the talk. So I had a question. What was the website that you used for benchmarking the different compilation times?
I pointed it out. It's, maybe I can go back. So if you click here, that will be the website.
All right, thank you.
All right, thank you.